recommend that protein intake make up only 10% of our daily calorie intake. Some people, especially in the United States and other developed countries, consume more protein than the body needs. Because extra amino acids cannot be stored for later use, the body destroys these amino acids and excretes their byproducts. Alternatively, deficiencies in protein consumption, seen in the diets of people in some developing nations, may result in health problems. Marasmus and kwashiorkor, both life-threatening conditions, are the two most common forms of protein malnutrition. Some health conditions, such as illness, stress, and pregnancy and breastfeeding in women, place an enormous demand on the body as it builds tissue or fights infection, and these conditions require an increase in protein consumption. For example, a healthy woman normally needs 45 grams of protein each day. Experts recommend that a pregnant woman consume 55 grams of protein per day, and that a breastfeeding mother consume 65 grams to maintain health. A man of average size should eat 57 grams of protein daily. To support their rapid development, infants and young children require relatively more protein than do adults. A 3-year-old infant requires about 13 grams of protein daily, and a 4-year-old child requires about 22 grams. Once in adolescence, sex hormone differences cause boys to develop more muscle and bone than girls. As a result, the protein needs of adolescent boys are higher than those of girls. 18. Fats, which provide 9 calories of energy per gram, are the most concentrated of the energy-producing nutrients, so our bodies need only very small amounts. Fats play an important role in building the membranes that surround our cells and in helping blood to clot. Once digested and absorbed, fats help the body absorb certain vitamins. Fat stored in the body cushions vital organs and protects us from extreme cold and heat. Fat consists of fatty acids attached to a substance called glycerol. Dietary fats are classified as saturated, monounsaturated, and polyunsaturated according to the structure of their fatty acids. Animal fats from eggs, dairy products, and meats are high in saturated fats and cholesterol, a chemical substance found in all animal fat. Vegetable fats found, for example, in avocados, olives, some nuts, and certain vegetable oils are rich in monounsaturated and polyunsaturated fat. As we will see, high intake of saturated fats can be unhealthy. To understand the problem with eating too much saturated fat, we must examine its relationship to cholesterol. High levels of cholesterol in the blood have been linked to the development of heart disease, strokes, and other health problems. Despite bad reputation, our bodies need cholesterol, which is used to build cell membranes, to protect nerve fibers, and to produce vitamin D and some hormones, chemical messengers that help coordinate the body's functions. We just do not need cholesterol in our diet. The liver, and to a lesser extent the small intestine, manufacture all the cholesterol we require. When cholesterol from foods that contain saturated fatty acids, we increase the level of a cholesterol-carrying substance in our blood that harms our health. Human diet should have more unsaturated fat because some unsaturated fatty acids cannot be synthesized from others. They are called essential fatty acids, e.g., linoleic acid, linolenic acid, arachidonic acid. Excessive lipids causes obesity, blood pressure and a number of cardiac problems. Daily requirement of adult is 50 gm. Vitamins. 19. Vitamins and minerals are needed by the body in very small amounts to trigger the thousands of chemical reactions necessary to maintain good health. Many of these chemical reactions are linked, with one triggering another. If a missing or deficient vitamin or mineral or link anywhere in this chain, this process may break down, with potentially devastating health effects. Although similar in supporting critical functions in the human body, vitamins and minerals have key differences. Among their many functions, vitamins enhance the body's use of carbohydrates, proteins, and fats. They're critical in the formation of blood cells, hormones, nervous system chemicals known as neurotransmitters, and the genetic material deoxyribonucleic acid DNA. Vitamins are classified into two groups, fat-soluble and water-soluble. Fat-soluble vitamins, which include vitamins A, D, E, and K, are usually absorbed with the help of foods that contain fat. Fat is broken down by bile, a liquid released by the liver, and the body then absorbs the breakdown products, and unsaturated fats has also been associated with greater risk of developing cancers of the colon, prostate, breast, and uterus. Using a diet that is low in fat and cholesterol is critical to maintaining health and reducing the risk of life-threatening disease. Excess amounts of fat-soluble vitamins are stored in the body's fat, liver, and kidneys. Because these vitamins can be stored in the body, they do not need to be consumed every day to meet the body's needs. Water-soluble vitamins, which include vitamin C, also known as ascorbic acid B1, thiamine, B2, riboflavin, B3, niacin, B6, B12, and folic acid, cannot be stored and rapidly leave the body in urine if taken in greater quantities than the body can use. Foods that contain water-soluble vitamins need to be eaten daily to replenish the body's needs. Role noted in the vitamin and mineral chart accompanying this article, vitamins A, in the form of beta-carotene C, and E function as antioxidants, which are vital in countering the potential harm of chemicals known as free radicals. If these chemicals remain unchecked, they can make cells more vulnerable to cancer-causing substances. Free radicals can also transform chemicals in the body into cancer-causing. Vitamin function deficiency source. Retinol. Yellow viscous oil antixerophthalmic. Synthesis of retinal pigments, maintenance of epithelia, prevention of keratinization, anti-infective. Xerophthalmia, night blindness, keratomalacia. Dermatosis, toad skin, stunted growth. Keratin in vegetables, mango, orange, and as such in milk, butter, ghee, egg yolk, liver oil. D. Sterile calciferol, 10 types, common D2 and D3. Antirachitic, absorption and retention of Ca and P. Rickets in children. Osteomalacia in adults, sunshine. E. Tocopherol. Collox oil, alpha and beta anti-sterility factor. Antioxidative for membrane lipids, skin, reduces keratinization, and hair, reduces atherosclerosis. Erythrocyte breakdown, anemia, muscular dystrophy, cramps, miscarriage, and reduced fertility. Green vegetables, oils, milk, cheese, butter, egg. K-phylloquinone, yellow oil and fat, K1 and K2. Anti-hemorrhagic factor, factor for synthesis of prothrombin, hence. Essential for blood coagulation, electron carrier, liver. Functioning. Prolonged bleeding, bleeding disease or hemorrhages. Liver malfunctioning. Green vegetables, tomato. Colon bacteria. Thiamine B1, vitamin G. Antineuritic, antiberiberi, component of TPP, functioning of muscles and nerves. Anorexia, muscular atrophy, beriberi in humans and polyneuritis in animals. Yeast, whole grains, egg yolk, liver. Riboflavin B2. Maintenance of skin and oral mucosa, component of FMN and FAD, anti-migraine. Glossus, glossitis, intolerance to light. Yeast, green vegetables, milk, curd, cheese, egg. Pantothenic acid B3, also B5. Formation of CoA, required in cell respiration. Functioning of skin and nerves. Gastrointestinal. Disorders, graying of hair in animals, burning feet syndrome. Yeast, milk, wheat bran, pulses, liver. Colon bacteria. Nicotinamide. Niacin, nicotinic acid N6. All B5, B7 vitamin POC pellagra preventive antipellagra, component of NAD+, NADP+, energy transfer and nervous system. Pellagra. Yeast, pulses, green vegetables, cereals, milk, egg yolk, liver. Pyridoxine B6 CPV. O. R. M. Id. P. O. O. X. N. A. E. L. N. P. H. O. O. C. P. E. A. Non-essential nutrients. 20. Cholesterol, like fat, is a lipid and organic compound that is not soluble in water. In order to travel through blood, cholesterol therefore must be transported through the body in special carriers, called lipoproteins. Density lipoproteins, HDLs, remove cholesterol from the walls of arteries, return it to the liver, and help the liver excrete it as bile, a liquid acid essential to fat digestion. For this reason, HDL is called good cholesterol. Low-density lipoproteins, LDLs, and very low-density lipoproteins, VLDLs, are considered bad cholesterol. Both LDLs and VLDLs transport cholesterol from the liver to the cells. As they work, LDLs and VLDLs leave plaque-forming cholesterol in the walls of the arteries, clogging the artery walls and setting the stage for heart disease. Almost 70% of the cholesterol in our bodies is carried by LDLs and VLDLs, and the remainder is transported by HDLs. For this reason, we need to consume dietary fats that increase our HDLs and decrease our LDL and VLDL levels. 21. Fatty acids found in foods ranging from beef to ice cream, to mozzarella cheese to donuts should make up no more than 10% of a person's total calorie intake each day. Saturated fats are considered harmful to the heart and blood vessels because they are thought to increase the level of LDLs and VLDLs and decrease the levels of HDLs. Monounsaturated fats found in olive, canola, and peanut oils appear to have the best effect on blood cholesterol, decreasing the level of LDLs and VLDLs and increasing the level of HDLs. Polyunsaturated fats found in margarine and sunflower, soybean, corn, and safflower oils are considered more healthful than saturated fats. However, if consumed in excess more than 10% of daily calories, they can decrease the blood levels of HDLs. Nutritional disorders. 21. Marasmus. It is a disorder caused by deficiency of food or protein energy malnutrition (PEM). Marasmus occurs in infants 1 to 2 years when they do not get sufficient mother's milk and weaning diet. Such infants are often provided with much diluted cow or buffalo milk. Marasmus shriveled appearance with thin face, sunken eyes, wrinkled and dry skin, protruding ribs, reduced digestion and frequent diarrhea, low weight, little growth and poor mental abilities. 22. Kwashiorkor. It is a protein energy malnutrition that occurs in children of 1 to 4 years due to constant reduced protein in diet. Due to I. Early stoppage of breast milk. E. Late supply of supplementary food. E. Overdiluted milk. IV. Maintaining children on cooking water of cereals. A kwashiorkor child has matchstick legs, protruded belly, blotchy skin, anemia, edema of certain parts and repeated diarrhea. 23. Obesity. Obesity is a luxury nutritional disorder caused by greater intake of food than the requirement of body. It is quite common in persons having higher intake of sweets, carbohydrate-rich food, fried articles, fat-rich food and absence of roughage in food. Obese persons are overweight with excessive accumulation of fat. Movements are reduced. There is a risk of diabetes, osteoarthritis, gallbladder stones, high blood pressure and cardiac problems. The reasons for overeating are psychogenic, physiological, genetic and developmental. 24. Hypercholesterolemia. It is characterized by high blood cholesterol due to higher intake of cholesterol-rich eggs, red meat, butter and ghee or reduced biotin intake. Cholesterol gets deposited on the walls of blood vessels making their lumen narrow and walls stiffer. This increases blood pressure or hypertension. It leads to other cardiovascular disorders. 25. Rickets. The disorder is due to deficient ossification of bone ends leading to their bending and swelling of joints, knee, wrist, elbow. For children of 6 months to 2 years when their diet is deficient in vitamin D, calcium or phosphorus. 26. Osteomalacia. The disorder occurs in adults when their food is deficient in vitamin D, calcium or phosphorus. Bones of vertebral column become weak. Pelvic and other bones bend and become soft. 27. Ear-ophthalmia. It is a vitamin A deficiency disorder which is caused by stoppage of lacrimal activity. Cornea and eyelids become dry and ulcerated. It leads to swelling of dry eyelids and opacity of cornea. Xerophthalmia, if untreated, leads to blindness. 28. Blindness. Nyctalopia. Dietary deficiency of vitamin A results in deficiency of rhodopsin or visual purple. The latter impairs the ability to see in dim light or night. 29. Beriberi. Beriberi is a debility produced by deficiency of thiamines during excessive intake of polished rice. It results in loss of appetite, anorexia, weakening of muscles, fatigue, poor digestion, palpitation, slow reflexes, body rigidity and neuritis. There is inflammation of peripheral nerves, weakening of muscles, paralysis and progressive edema. Depending upon the system affected, beriberi is of 5 types: dry, wet, mixed, cardiac and cerebral. 30. Scurvy. Vitamin C, ascorbic acid deficiency leads to scurvy characterized by bleeding gums, falling of teeth, fragile blood vessels, fragile bones and slow healing of injuries. 31. Anemia. It is a disorder in which hemoglobin content of the blood is low due to either few red blood corpuscles or their hemoglobin content. It is of 3 types. Microcytic, most common, due to iron deficiency leading to fewer and smaller erythrocytes with reduced hemoglobin. Megablastic due to fewer abnormal, red blood cells caused by deficiency of folic acid or B12. Pernicious due to production of hemoglobin-free immature RBCs caused by B12 deficiency as a result of deficient intrinsic factor. Sickle cell anemia and thalassemia are genetically controlled. Anemia also occurs due to excessive blood loss. The same is called posthemorrhagic anemia. 32. Minerals. Sodium. It is a cation of extracellular fluid, component of bile salts which is involved in osmotic balance, acid-basic balance, absorption of glucose, electrochemical impulse conduction in nerves and muscles. It is main cation of extracellular fluid, component of bile salts which is involved in osmotic balance, acid-basic balance, absorption of glucose, electrochemical impulse conduction in nerves and muscles. Deficiency produces cramps. Chlorine, main anion of extracellular fluid, involved in HCl synthesis and acid-basic balance. Potassium, the cation is present in intracellular as well as extracellular fluid. It takes part in muscle and nerve activity, glycogen and protein synthesis. Magnesium, it is an enzyme activator, component of bones and teeth besides being required for muscle relaxation. Deficiency produces convulsions. Sulfur, it is a constituent of many proteins. Enzymes and coenzymes. Cobalt, a component of 12. Deficiency causes pernicious anemia. Fluorine, maintains enamel and checks dental decay, in excess harmful to teeth and bones. Calcium, it is a major component of bones and teeth. It's required for blood clotting, muscle contraction, ATPase, nerve impulse transmission, heart functioning, etc. Vitamin D is essential for calcium absorption. Deficiency produces rickets and muscle spasms. Phosphorus, along with calcium, it occurs in bones and teeth. Phosphorus is a component of nucleic acids, phospholipids, ATP and some coenzymes. Phosphorylation activates sugars and fatty acids. Phosphate is pH buffer. Deficiency reduces growth, metabolism and causes rickets in children along with calcium and vitamin D. Iron, it is reused in the body. Iron is a component of hemoglobin, myoglobin, cytochromes and ferredoxin. Deficiency leads to anemia. Iodine, it is essential for production of hormone thyroxine of thyroid glands. Deficiency causes goiter. Selenium, essential for protecting sperms and hence maintenance of male fertility. C. Stabilizing interactions. Covalents are very stable because the energies required to break them are much greater than the thermal energy available at room temperature, 25 C, or body temperature, 37 C. For thermal energy at 25 C is approximately 0.6 kilocalorie per mole, whereas the energy required to break the carbon-carbon single bond, Cc, in ethane is about 140 times larger. at room temperature 25 C fewer than 1 in 1012 ethane molecules is broken into a pair of CH3 radicals, each containing an unpaired, non-bonding electron. Covalent single bonds in biological molecules have energies similar to that of the CC bond in ethane. Because more electrons are shared between atoms in double bonds, they require more energy to break than single bonds. For instance, it's 84 kilocalories per mole to break a single CC bond, but 170 kilocalories per mole to break a C equals O double bond. The common double bonds in biological molecules are C equals O, C equals N, C equals C, and P equals O. The energy required to break noncovalent interactions is only 1 to 5 kcal per mole, much less than the bond energies of covalent bonds. Indeed, noncovalent interactions are weak enough that they are constantly being formed and broken at room temperature. Although systems are weak and have a transient existence at physiological temperatures, 25 to 37 C, multiple noncovalent interactions can act together to produce highly stable and specific associations between different parts of a large molecule or between different macromolecules. We first review the 4 main types of noncovalent interactions and then consider their role in the binding of biomolecules to one another and to C1. Van der Waals interactions. When any two atoms approach each other closely, they create a weak, non-specific attractive force that produces a van der Waals interaction, named for Dutch physicist Johannes Diederik van der Waals, 1837-1923, who first described it. These non-specific interactions result from the momentary random fluctuations in the distribution of the electrons of any atom, which give rise to a transient unequal distribution of electrons, that is, a transient electric dipole. If covalently bonded atoms are close enough together, the transient dipole in one atom will perturb the electron cloud of the other. This perturbation generates a transient dipole in the second atom, and the two dipoles will attract each other weakly. Similarly, a polar covalent bond in one molecule will attract an oppositely oriented dipole in another. Van der Waals interactions, involving either transient-induced or permanent electric dipoles, occur in all types of molecules, both polar and nonpolar. In particular, Van der Waals interactions are responsible for the cohesion between molecules of nonpolar liquids and solids, such as heptane, CH3, CH2, 5CH3, that cannot form hydrogen bonds or ionic interactions with other molecules. When these stronger interactions are present, they override most of the influence of Van der Waals interactions. Heptane, however, would be a gas if Van der Waals interactions could not form. Strength of Van der Waals interactions decreases rapidly with increasing distance, thus these noncovalent bonds can form only when atoms are quite close to one another. However, if atoms get too close together, they become repelled by the negative charges in their outer electron shells. When the van der Waals repulsion between two atoms exactly balances the repulsion between their two electron clouds, the atoms are said to be in van der Waals. Each type of atom has a van der Waals radius at which it is in van der Waals contact with other atoms. The van der Waals radius of an H atom is 0.1 nanometers, and the radii of O, N, C, and S atoms are between 0.14 and 0.18 nanometers. Two covalently bonded atoms are closer together than two atoms that are merely in van der Waals contact. For van der Waals interaction, the internuclear distance is approximately the sum of the corresponding radii for the two participating atoms. Thus the distance between a atom and an H atom in van der Waals contact is 0.27 nanometers, and between two C atoms is 0.34 nanometers. In general, the van der Waals radius of an atom is about twice as long as its covalent radius. For example, ACH covalent bond is about 0.107 nanometers long and ACC covalent bond is about 0.154 nanometers long. The energy of van der Waals interaction is about 1 kilocalorie per mole, only slightly higher than the average thermal energy of molecules at 25 degrees Celsius. Van der Waals interactions, as well as other noncovalent bonds, mediate the binding of many enzymes with their specific substrates, the substances on which an enzyme acts, and of each type of antibody with its specific antigen. C2. Electrostatic ionic interactions. In some cases, the bonded atoms are so different in electronegativity that the bonding electrons are never shared. These electrons are always found around the more electronegative atom. In sodium chloride NaCl, for example, the bonding electron contributed by the sodium atom is completely transferred to the chlorine atom. Even solid crystals of NaCl, the sodium and chlorine atoms are ionized, so it is more accurate to write the formula for the compound as Na plus Cl. Because the electrons are not shared, the bonds in such compounds cannot be considered covalent. Rather, ionic bonds or interactions that result from the attraction of a positively charged ion a cation for a negatively charged ion an anion. Unlike covalent or hydrogen bonds, ionic bonds do not have fixed or specific geometric orientations because the electrostatic field around an ion. Its attraction for an opposite charge is uniform in all directions. However, crystals of salts such as Na plus Cl do have very regular structures because that is the energetically most favorable way of packing together positive and negative ions. The force that stabilizes ionic crystals is called the lattice energy. In aqueous solutions, simple ions of biological significance, such as Na+, K+, Ca2+, Mg2+, and Cl, do not exist as free, isolated entities. Instead, each is surrounded by a stable, tightly held shell of water molecules. An ion interaction occurs between the ion and the oppositely charged end of the water dipole, as shown below for the K+ ion. Ions play an important biological role when they pass through narrow, protein-lined pores, or channels, in membranes. For example, ionic movements through membranes are essential for the conduction of nerve impulses and for the stimulation of muscle contraction. The ions must enter a shell of water molecules in order to pass through ion channel proteins. Channel proteins can then selectively admit only Na+, or K+, or Ca2+ ions, a selectivity essential for nerve function. Most ionic compounds are quite soluble in water because a large amount of energy is released when ions tightly bind water molecules. This is known as the energy of hydration. Oppositely charged ions are shielded from one another by the water and tend not to recombine. Salts like Na plus Cl dissolve in water because the energy of hydration is greater than the lattice energy that stabilizes the crystal structure. In contrast, certain salts, such as Ca3PO42, are virtually insoluble in water. The large charges on the Ca2+ and PO43 ions generate a formidable lattice energy that is greater than the energy of hydration. C3. The hydrogen bond. Normally, a hydrogen atom forms a covalent bond with only one other atom. However, a hydrogen atom covalently bonded to a donor atom, D, may form an additional weak association, the hydrogen bond, with an acceptor atom, A. In order for a hydrogen bond to form, the donor atom must be electronegative, so that the covalent DH bond is polar. The acceptor atom also must be electronegative, and its outer shell must have at least one non-bonding pair of electrons that attracts the D+ charge of the hydrogen atom. Biological systems, both donors and acceptors are usually nitrogen or oxygen atoms, especially those atoms in amino NH2 and hydroxyl O groups. Because all covalent NH and OH bonds are polar, their H atoms can participate in hydrogen bonds. By contrast, CH bonds are nonpolar, so these H atoms are almost never involved in a hydrogen bond. Water molecules provide a classic example of hydrogen bonding. The hydrogen atom in one water molecule is attracted to a pair of electrons in the outer shell of an oxygen atom in an adjacent molecule. In turn, molecules with polar bonds that easily form hydrogen bonds with water can dissolve in water and are said to be hydrophilic, Greek, water-loving. Besides the hydroxyl and amino groups, peptide and ester bonds are important chemical groups that interact well with water. Hydrogen bonds are 0.26–0.31 nanometers long, about twice the length of covalent bonds between the same atoms. In particular, the distance between the nuclei of the hydrogen and oxygen atoms of adjacent hydrogen-bonded molecules in water is approximately 0.27 nanometers, about twice the length of the covalent OH bonds in water. The hydrogen atom is closer to the donor atom, D, to which it remains covalently bonded, than it is to the acceptor. The length of the covalent DH bond is a bit longer than it would be if there were no hydrogen bond, because the acceptor pulls the hydrogen away from the donor. The strength of a hydrogen bond in water 5 kcal per mole is much weaker than a covalent OH bond, approximately equals 110 kilocalories per mole. Hydrogen bonds is a major stabilizing force in macromolecules. An important feature of all hydrogen bonds is directionality. The strongest hydrogen bonds, the donor atom, the hydrogen atom, and the acceptor atom all lie in a straight line. Nonlinear hydrogen bonds are weaker than linear ones. The strengths of the hydrogen bonds in proteins and nucleic acids are only 1–2 kilocalories per mole, considerably weaker than the hydrogen bonds between water molecules. Initially, both the NH2 groups in the protein are hydrogen bonded to water, and the formation of a hydrogen bond between these groups involves disruption of their hydrogen bonds with water. Thus, net change in energy in forming this ON hydrogen bond will be less than the 5 kilocalories per mole characteristic of hydrogen bonds between water molecules. C4. Hydrophobic interactions. Nonpolar molecules do not contain ions, possess a dipole moment, or become hydrated. Because such molecules are insoluble or almost insoluble in water, they are said to be hydrophobic, Greek, water-fearing. The covalent bonds between two carbon atoms and between carbon and hydrogen atoms are the most common nonpolar bonds in biological systems. Hydrocarbons molecules made up only of carbon and hydrogen are virtually insoluble in water. A large triacetyl or triglyceride, such as tristyrene, a component of animal fat, is also insoluble in water, even though its 6 oxygen atoms participate in some slightly polar bonds with adjacent carbon atoms. When shaken in water, tristyrene forms a separate phase similar to the separation of oil from a water-based vinegar in an oil and vinegar salad dressing. The force that causes hydrophobic molecules or nonpolar portions of molecules to aggregate together rather than to dissolve in water is called the hydrophobic bond. This is not a separate bonding force, rather, it is the result of the energy required to insert a nonpolar molecule into water. A polar molecule cannot form hydrogen bonds with water molecules, so it distorts the usual water structure, forcing the water into a rigid cage of hydrogen-bonded molecules around it. Water molecules are normally in constant motion, and the formation of such cages restricts the motion of a number of water molecules. The effect is to increase the structural organization of water. This situation is energetically unfavorable because it decreases the randomness entropy of the population of water molecules. The opposition of molecules to having their motion restricted by forming cages around hydrophobic molecules or portions thereof is a major reason molecules such as tristyrene and heptane are essentially insoluble in water and interact mainly with other hydrophobic molecules. Nonpolar molecules can also bond together, albeit weakly, through van der Waals interactions. The net result of the hydrophobic and van der Waals interactions is a very powerful tendency for hydrophobic molecules to interact with one another, and not with water. The order of hydrophobic character for various amino acids is as follows. Hydrophobic. Glycine less than tyrosine less than alanine less than histidine less than methionine less than valine less than leucine less than isoleucine less than phenylalanine less than tryptophan. All hydrocarbons like butane, CH3, CH2, CH2, CH3, are somewhat soluble in water, because they can dissolve without disrupting the water lattice appreciably. However, 1-butanol, CH3, CH2, CH2, CH2O, mixes completely with water in all proportions. The replacement of just one hydrogen atom with the polar O group allows a molecule to form hydrogen bonds with water and greatly increases its solubility. Simply put, like dissolves like. Polar molecules dissolve in polar solvents such as water, while nonpolar molecules dissolve in nonpolar solvents such as hexane. Molecular complementarity permits tight, highly specific binding of biomolecules. Both inside and outside of cells, ions and molecules are constantly bumping into one another. The greater the number of copies of any two types of molecules per unit volume, i.e., the higher their concentration, the more likely they are to encounter one another. When two molecules encounter each other, they most likely will simply bounce apart because the noncovalent interactions that would bind them together are weak and have a transient existence at physiological temperatures. However, molecules that exhibit molecular complementarity, a lock and key kind of fit between their shapes, charges, or other physical properties, can form multiple noncovalent interactions at close range. When two such structurally complementary molecules bump into each other, they can bind, stick together. It illustrates how multiple, different weak bonds can bind two proteins together. Most any other arrangement of the same groups on the two surfaces would not allow the molecules to bind so tightly. Multiple, specific interactions between complementary regions within a protein molecule allow it to fold into a unique three-dimensional shape and hold the two chains of DNA together in a double helix. Similar interactions underlie the association of groups of more than two molecules into multimolecular complexes, leading to formation of muscle fibers, to the glue-like associations between cells in solid tissues, and to numerous other cellular structures. Depending on the number and strength of the non-covalent interactions between the two molecules and on their environment, their binding may be tight, strong, or loose, weak, and, as a consequence, either long-lasting or transient. The higher the unity of two molecules for each other, the better the molecular fit between them, the more non-covalent interactions can form, and the tighter they can bind together. An important quantitative measure of affinity is the binding dissociation constant Kd. Nearly all the chemical reactions that occur in cells also depend on the binding properties of enzymes. Enzymes not only speed up reactions but also do so with a high degree of specificity, a reflection of their ability to bind tightly to only one or a few related molecules. And binding specificity of large biological molecules, particularly proteins and nucleic acids, is one of the distinctive features that distinguish biochemistry from typical solution chemistry. Clearly, molecular complementarity and non-covalent interactions underlie the structures of biomolecules and many processes critical to life. D. Principles of biophysical chemistry. D1. Water, pH and buffers. Water is essential to biochemistry because biological macromolecules assume specific shapes in response to the chemical and physical properties of water. B. Biological molecules undergo chemical reactions in an aqueous environment. C. Water is a key reactant in many reactions, usually in the form of H+ and O ions. Water is oxidized in photosynthesis to produce molecular oxygen, O2, as part of the process that converts the sun's energy into usable chemical form. Expenditure of that energy under aerobic conditions leads to the reduction of O2 back to water. Physical properties of water. 1. The structure of water closely approximates a tetrahedron with its two hydrogen atoms and the two lone pairs of electrons of its oxygen atom, occupying the vertices of the tetrahedron. 2. The high electronegativity of oxygen relative to hydrogen results in the establishment of a permanent dipole in water molecules. 3. Polar nature of water results in negative portions of the molecule being attracted to the positive portions of neighboring water molecules by a largely electrostatic interaction known as the hydrogen bond. 4. Hydrogen bond represented as D, HA, where D, H is a weakly acidic compound so that the hydrogen atom H has a partial positive charge, and A is a weakly basic group that bears lone pairs of electrons. A is often an oxygen atom or a nitrogen atom, occasionally sulfur. 5. Water is strongly hydrogen bonded, with each water molecule participating in 4 hydrogen bonds with its neighbors, 2 in which it donates and 2 in which it accepts. Hydrogen bonds commonly form between water molecules and the polar functional groups of biomolecules, or between the polar functional groups themselves. 6. The strongly hydrogen bonded character of water is responsible for many of its characteristic properties, most notably high heat of fusion, which allows water to act as a heat sink, such that greater heat loss is necessary for the freezing of water compared to other substances of similar molecular mass. A high heat of vaporization, such that relatively more heat must be input to vaporize water compared to other substances of similar molecular mass. C. An ability to dissolve most polar compounds. D. An open structure makes ice less dense than liquid water, thereby making ice float, insulating the water beneath it, and inhibiting total freezing of large bodies of water. 7. A variety of weak electrostatic interactions are critical to the structure and reactivity of biological molecules. These interactions include, in order of increasing strength, London dispersion forces, dipole-dipole interactions, hydrogen bonds, and ionic interactions. 8. Water is an excellent solvent of polar and ionic substances due to its property of surrounding polar molecules and ions with oriented shells of water, thereby attenuating the electrostatic forces between these molecules and ions. 9. The tendency of water to minimize its contact with nonpolar, hydrophobic molecules is called the hydrophobic effect. This effect is largely driven by the increase in entropy caused by the necessity for water to order itself around nonpolar molecules. This causes the nonpolar molecules to aggregate, thereby reducing the surface area that water must order itself about. Consequently, nonpolar substances are poorly soluble in aqueous solution. 10. Many biological molecules have both polar or charged and nonpolar functional groups and are therefore simultaneously hydrophilic and hydrophobic. These molecules are said to be amphiphilic or amphipathic. 11. Osmosis is the movement of solvent across a semipermeable membrane from a region of lower concentration of solute to a region of higher concentration of solute. Osmotic pressure of a solution is the pressure that must be applied to the solution to prevent an inflow of solvent. Hence, an increase in solute concentration results in an increase in osmotic pressure. 12. Diffusion is the random movement of molecules in solution or in the gas phase. It is responsible for the movement of solutes from a region of high concentration to a region of low concentration. Chemical properties of water. 1. Water is a neutral, polar molecule that has a slight tendency to ionize into H+ and OH. However, the proton is never free and binds to a water molecule to form H3O+ hydronium ion. 2. The ionization of water is described as an equilibrium between the unionized water reactant and its ionized species products. Acidic solution. The concentration of water is essentially constant 55.5 m. The concentration of H2O is incorporated into the value of K, which is referred to as Kw, the ionization constant of water. 3. The values both H+ and K are inconveniently small, hence, their values are more conveniently expressed as negative logarithms, so that pH equals log H+, pK equals log K. 4. According to Bronsted-Lowry definition, an acid is a substance that can donate a proton, and a base is a substance that can accept a proton. The strength of a weak acid is proportional to its dissociation constant, which is expressed as 5. pH of a solution of a weak acid is determined by the relative concentrations of the acid and its conjugate base. The equilibrium expression for the dissociation of a weak acid can be rearranged to. This relationship is known as the Henderson-Hasselbalch equation. When the concentration of a weak acid is equal to the concentration of its conjugate base, pH equals pK. Hence, the stronger the acid, the lower its pK. 6. Solutions of a weak acid at Fis near its pK resist large changes in pH as OH or H+ is added. Protons react with the weak acid's conjugate base to reform the weak acid, whereas added OH combines with the acid to form its conjugate base in water. A solution of a weak acid and its conjugate base, in the form of a salt, is referred to as a buffer. Buffers are effective within 1 picohenry unit of the pK of the component acid. 7. The properties of most proteins, enzymes for example, are sensitive to pH. As the pH drops, H+ bind to the carboxyl groups COO of aspartic acid ASP and glutamic acid GLU, neutralizing their negative charge, and H+ bind to the unoccupied pair of electrons on the N atom of the amino NH2 groups of lysine Li and arginine ARG, giving them a positive charge. Not only does the net charge on the molecule change, it becomes more positive, but many of the opportunities that its R groups have for ionic electrostatic interactions with other molecules and ions are altered. 8. As the pH rises, H+ are removed from the COOH groups of asp and GLU, giving them a negative charged COO, and H+ are removed from the NH3+ groups of Li and ARG, removing their positive charge. The result, again, net charge on the molecule changes, it becomes more negative, and, again, many of the opportunities its R groups have for electrostatic interactions with other molecules or ions are altered. 9. The pH of the cytosol within a human cell is about 7.4. But, this value masks the pH differences that are found in various compartments within the cell. For example, the interior of lysosomes is much more acidic, as low as pH 4 to 5, than the cytosol, and the enzymes within work best at these low pH values. 10. The pH differential created within chloroplasts by the energy of the sun is harnessed to synthesize ATP, which, in turn, powers the synthesis of food. The differential created within mitochondria during the respiration of food is harnessed to the synthesis of ATP, which, in turn, powers most of the energy-consuming activities of the cell, such as locomotion and biosynthesis of cell components. 11. A tenfold change in H+ alters the pH by 1.0 unit. 12. Buffers. A buffer is a mixture of a weak acid and the salt of that acid. The practical buffer zone is pKa plus 1 picohenry. The Henderson-Hasselbalch equation is used for calculations involving buffers. pH equals pKa plus log A. Ha. pH of a buffer is theoretically independent of dilution, depends only on the ration of A, HA and pKa. 13. Solving pH problems. Strong acids completely dissociated. H equals normality of acid, pH equals log H plus, strong bases. H is normality of acid, pH equals log H plus, strong bases completely dissociated. OH equals normality of base, PO equals log OH, pH plus PO equals 14. Weak acids, two kinds of problem. A, percent ionization X molarity equals H plus. B, Ka equals H plus A equals X2 tilde X2. Ha X equals H plus equals Ka X ha. D2. Kinetics, dissociation and association constants. 1. The branch physical chemistry in which we study rate of reaction and mechanism of the reaction is known as chemical kinetics. 2. Rate of reaction. The rate of the reaction may be defined as the rate of change of the concentration of the reactants with time. In other words, it is measured by the amount of substance in unit volume changed in unit time, and amount is measured in mole. Thus, rate of reaction equals amount transformed. Time taken in transformation equals dx dt, where dx is the amount of substance changed and dt is a very small interval of time. Negative sign indicates that velocity of the reaction decreases with time. It is important to note that the concept of mechanical velocity or speed cannot be used in measuring the rate of reaction. Because rate of reaction depends upon the molar concentrations of the reactants and it decreases with time, therefore rate of reaction varies with time. 3. Factors influencing rate of reaction. I. Effect of concentration. The rate of a reaction decreases with decrease of concentration. E. Effect of temperature. It is observed that rate of a reaction increase with rise of temperature. In general, rate of a reaction becomes double on rise of 10 C, usually 25-35 degrees Celsius. E. The nature of reactant. It is observed that the reactions in which simple ions are involved take place faster than the reactions in which ions of considerable bonds are involved. For example, oxidation of Fe2+ ion by permanganate ion MnO4 ion in acidic medium takes place faster than the oxidation of C2O4 ion under same conditions. IV. Effect of catalyst. In general, catalyst increases the rate of reaction. B. Effect of surface area of reactants. It is observed that the smaller particles react more rapidly than the larger particles of the same mass. For example, coal dust bumps rapidly than that of large lumps of coal. P. Effect of radiation. Rate of certain reactions increases by the absorption of photons of certain radiations. Such reactions are known as photochemical reactions. 4. Constant. According to collision theory, the rate of the reaction is proportional to the number of molecular collisions taking place per second. Thus, on increasing the concentration of the reactant, number of collisions increases, hence rate of the reaction increases. Thus, for a general reaction, A products. R equals dx dt equals dCA dt equals kCA. Where R equals rate of reaction, Ca equals concentration of the reactant A and K equals rate constant. If Ca equals 1, then R equals K. We can say that at a given temperature, rate is equal to the rate constant of reaction when concentration of the reactant is unity. Thus rate constant is known as specific reaction rate. In the case of two reactants, the reaction may be written as A plus B products. R equals dx dt equals KCACB, where all the terms have usual meaning. If Ca equals Cb equals 1, then R equals K. The rate constant is equal to rate of the reaction when concentration of each of the reactants is unity. 5. Order of a reaction. Chemical reactions may be classified on the basis of the number of molecules that must ultimately react to form the reaction products. Thus we have monomolecular, bimolecular, and trimolecular reactions, in which 1, 2 or 3 molecules, respectively, undergo reaction. Chemical classified on a kinetic basis by reaction order such as zero order, first order, second order, and third order reactions, depending on how the reaction rate is influenced by the concentration of the reactants under a given set of conditions. 6. Zero order reactions. If the rate of reaction is independent of the concentration of the reactant, then the reaction is called zero order reaction. For example, a product R equals dC0A dt equals K. If A equals initial concentration, X equals amount decomposed in time, then T X T AAXK equals minus 7. First order reactions. If the rate of a reaction is determined by the variation of concentration term of only one reactant, then the reaction is called first order reaction. For example, a product R equals dCA dt equals KCA. dC8Ca equals KdT. The integrated form of the first order rate equation is C T K equals 2.303 log 0, where Co and K are concentration at initial time, i.e., T equals O, and at any subsequent time respectively. If the initial concentration of the reactant is a mol LL and after time T, X mol LL have reacted to give the product, then the concentration of the reactant left behind at the time T will be AX moles LL. Then the first order rate equation may be given as XA A T K minus equals log 2.303. In first order reaction, the half time T1 half of the reaction is given by T1 half equals 0.693 K. Here, the half time is independent of the initial concentration of the substrate. T1 half is defined as the time during which half the concentration of a given reactants react. First order rate constants have the dimensions of reciprocal time, usually sec L. 8. For reactions, a reaction is said to be of the second order if its rate is determined by the variation of two concentration terms. The rate of the reaction is proportional to the second power of the concentration of a single substance. In general, the second order reactions may be of two types. A. When the concentration of the reactants is same, i.e. A plus A products. Let A be the initial concentration of each of the reactants to start the reaction and X be the amount of each reactant decomposed after time, T. 2 A products. A zero initial concentration AXX concentration after time T. The rate of the reaction may be represented by K dt AX dx minus 2 equals. On integration within the limits 0 to X at time 0 to T respectively, we get opening parenthesis closing parenthesis 1 AAX XX T K minus equals B, when the concentration of the reactants is different, i.e. A plus B product. AB0 initial concentration AXBXX concentration after time T, the rate of reaction will be expressed as KAXBX dt dx equals minus K dt AXBX dx opening parenthesis closing parenthesis closing parenthesis equals minus. On integration within the limits 0 to X at time 0 to T respectively. BXA AXB TAB K opening parenthesis closing parenthesis log 10 2.303 minus equals. The rate constants of second order reactions have the dimensions 1 concentration X time or mol minus 1 second minus 1. 9. Third order reactions. A reaction is said to be of third order if the rate is determined by the variation of 3 concentration terms. In other words, the minimum number of molecules necessary for the reaction to take place is 3. There may be 3 different cases in third order reaction. A. All the 3 species have equal concentrations. A plus AP. Consider a general reaction involving 3 moles of A having the concentration of each as A moles per liter. Let the concentration at time T becomes AX, then the rate of reaction is given by KAX3 dt dx equals minus. The integrated form of the equation is 2 A2AX AX T K minus equals B, when the concentrations of 2 reactants are unequal and are different. 2A plus B products. The rate of reaction is given by 2KAX2BX dt dx equals minus. In order to know the values of K, integrating above equation, we get minus plus minus equals opening parenthesis closing parenthesis 2 log opening parenthesis closing parenthesis 2 1 2ABX BAZ AAX XBA TAB K. The rate constants of third-order reactions have the dimensions mole minus 2L 2 seconds minus 1. D3. Thermodynamics. 1. Matter is anything that has mass and takes up space. Energy is the capacity to do work, that is, to move matter against opposing forces, such as gravity and friction. 2. Anything that moves possesses a form of energy called kinetic energy. Any moving object, including an atom or molecule, has kinetic energy, the energy of motion. Heat, or thermal energy, is kinetic energy that results from the random movement of molecules. Light also represents energy, which can be harnessed to perform work, such as powering photosynthesis in green plants. 3. A resting object, not presently at work, may also possess energy, which is the capacity to do work. Stored energy, or potential energy, is energy that matter possesses because of its location or arrangement. Water behind a dam, for instance, stores energy because of its altitude. Energy, a form of potential energy especially important to biologists, is stored in molecules because of the arrangement of the atoms that are bonded together. 4. Energy transformations. Energy can be converted from one form to another. Chemical energy tapped when chemical reactions rearrange the atoms of molecules in such a way that potential energy stored in the molecules is converted to kinetic energy. The chemical energy stored in the fuel molecules had itself been converted from light energy by plants during photosynthesis. 5. Free is the portion of a system's energy that can perform work when temperature is uniform throughout the system, as in a living cell. A system's quantity of free energy is symbolized by the letter G. There are two components to G, the system's total energy, symbolized by H, and its entropy, symbolized by S. Free energy is related to these factors in the following way. G equals HTS. Stands for absolute temperature, OC plus 273. Notice that temperature amplifies the entropy term of the equation. 6. In any spontaneous process, the free energy of a system decreases. The change in free energy as a system goes from a starting state to a different state is represented by increment G. Increment G equals G final state, G starting state. Or put another way, increment G equals increment HT increment S. 7. Study of the energy transformations that occur in a collection of matter is called thermodynamics. Scientists use the word system to denote the collection of matter under study and refer to the rest of the universe, everything outside the system, as the surroundings. 8. A closed system, such as that approximated by liquid in a thermos bottle, is isolated from its surroundings. In an open system, energy can be transferred between the system and its surrounding. Organisms are open systems. Light energy or chemical energy in the form of organic molecules and release heat and metabolic waste products, such as carbon dioxide, to the surroundings. 9. According to the first law of thermodynamics, the energy of the universe is constant. Energy can be transferred and transformed, but it cannot be created or destroyed. The first law is also known as conservation of energy. The hydropower station does not create energy but convert potential energy stored in water into electrical energy when falling water moves the turbines. 10. The second law of thermodynamics can be stated in many ways. Let's begin with the following concept. Every energy transfer or transformation makes the universe more disordered. There is a quantitative measure of disorder, called entropy, whose value increases as disorder increases. We can now state the second law as follows. Every energy transfer or transformation increases the entropy of the universe. There is an unstoppable trend towards randomization. In many cases, increased entropy is evident in the physical disintegration of a system's organized structure. Consider, for example, the degradation of an unmaintained building. Much of the increasing entropy of the universe is less apparent, however, because it takes the form of an increasing amount of heat, which is the energy of random molecular motion. 11. Turn of other forms of energy to heat does not violate the first law of thermodynamics. Energy has been conserved, because heat is a form of energy, albeit in its random state. By combining the first and second laws of thermodynamics, we conclude that the quantity of energy in the universe is constant, but its quality is not. In a sense, heat is the lowest rate of energy, because it is an uncoordinated movement of molecules that many systems cannot harness in order to perform work. A system can only put heat to work when there is a temperature difference that results in the heat flowing from a warmer location to a cooler one. If temperature is uniform throughout a system, as it is in a living cell, then the only use for heat energy is to warm a body of matter, such as an organism. 12. Thus, an organism takes in organized forms of matter and energy from the surroundings and replaces them with less ordered forms. For example, an animal obtains starch, proteins, and other complex molecules from the food it eats, and in turn releases carbon dioxide and water, relatively small and simple molecules that store less chemical energy than the food. The depletion of chemical energy is accounted by heat generated during metabolism. 13. Cells create ordered structures from less organized starting materials. Complex organisms evolve from simpler ancestors. But if organization in no way violates the second law, because the entropy of a particular system, such as an organism, may actually decrease, as long as the total entropy of the universe, the system plus its surroundings, increases. Thus, organisms are islands of low entropy in an increasingly random universe. The evolution of biological order is perfectly consistent with the laws of thermodynamics. 14. Bioenergetics or biochemical thermodynamics deals with the study of energy changes, transfer and utilization in biochemical reactions. The reactions are broadly classified as exergonic, energy-releasing, and endergonic, energy-consuming. Bioenergetics is concerned with the initial and final states of energy component of the reactants and not the mechanism of chemical reactions. 15. Free energy, the energy actually available to do work utilizable, is known as free energy. Changes in the free energy increment G are valuable in predicting the feasibility of chemical reactions. The reactions can occur spontaneously if they are accompanied by decrease in free energy. 16. During a chemical reaction, heat may be released or absorbed. Enthalpy increment H is a measure of the change in heat content of the reactants compared to products. 17. Entropy increment S represents a change in the randomness or disorder of reactants and products. Entropy attains a maximum as the reaction approaches equilibrium. The relation between the changes of free energy increment G, enthalpy increment H, and entropy increment S is expressed as increment G equals increment H, T increment S. 18. Termed free energy represented by increment GO, note the superscript O is often used. It indicates the free energy change when the reactants or products are at a concentration of 1 mol L at pH 7.0. Positive increment G. If free energy change increment G is represented by a negative sign, there is a loss of free energy. The reaction is said to be exergonic and proceeds spontaneously. On the other hand, a positive increment G indicates that energy must be supplied to the reactants. The reaction cannot proceed spontaneously and is endergonic in character. The hydrolysis of ATP is a classical example of exergonic reaction. 8 plus HAT plus pi increment GO equals minus 7.3 cal per mole. The reversal of the reaction ATP plus ADP plus pi increment GO equals minus 7.3 cal per mole. The reversal of the reaction ADP plus pi ATP is endergonic and occurs only when there is a supply of energy of at least 7.3 cal per mole. Increment GO is positive. 20. The free energy change becomes 0. Increment G equals O when a reaction is at equilibrium. At a constant temperature and pressure, increment G is dependent on the actual concentration of reactants and products. Conversion of reactant A to product B, AB, the following mathematical relation can be derived. Increment G equals increment GO plus RT lane B. Where increment GO equals standard free energy change, R equals gas constant, 1.987 cal per mole. T equals absolute temperature, 273 plus degree C. Lane equals natural logarithm. B equals concentration of product. AI equals concentration of reactant. 21. Energy producing and energy utilizing systems. Catabolic pathways, generation of energy by transformation, glycolysis, or oxidation, oxidative phosphorylation, of ingested or stored fuels. Anabolic pathways, utilization of energy for biosynthetic purposes, DNA synthesis, protein synthesis, etc. ATP, the link between the two pathways. Phosphoanhydride bonds, P, is high energy bonds, approximately 7 kilocalories per mole. Other nucleotides which are used as energy currency. A. GTP, gluconeogenesis. C. UTP, glycogen synthesis. These all depend on ATP formation. Enzyme nucleoside diphosphate kinase utilize ATP to convert GTP, CTP or UTP. Some other energy-rich bonds having a high free energy of hydrolysis greater than 7 kilocalories per mole. A. 1. 3-bis-phosphoglycerate mixed acid anhydrides. B. Phosphoenol pyruvate enol phosphates circa. Creatine phosphate phosphogonadines D. Pyrophosphate phosphoric acid anhydrides D. Acetyl-CoA thiol esters. D4. Colligative properties. Properties of solutions that depend on the number of molecules present and not on the kind of molecules are called colligative properties. These properties include boiling point elevation, freezing point depression, and osmotic pressure. Historically, colligative properties have been one means for determining the molecular weight of unknown compounds. In this chapter we discuss using colligative properties to measure the molecular weight of polymers. Because colligative properties depend on the number of molecules, we expect, and will show, that colligative property experiments give a number average molecular weight. Relative lowering of vapor pressure. As seen earlier. Or. For dilute solution, NV is negligible in comparison with Na. Or. By experimentally measuring relative lowering of vapor pressure in a solution of known mass of solute and molar mass of solvent and its weight, molar mass of solute can be determined. If Wa is mass of solvent in kilogram, then is molality of solution in Ma 1. i.e. elevation and boiling. Hence, we can say that relative lowering of vapor pressure is a colligative property as colligative properties are proportional to molality. Elevation and boiling point. Before understanding the elevation and boiling point, we should know what is boiling point. Boiling point of a liquid can be defined as that temperature at which its vapor pressure becomes equal to that of the atmospheric pressure. A solution of non-volatile solute has higher boiling point than solvent. Elevation and boiling point. As containing non-volatile solute has lower vapor pressure than solvent, the boiling point of solution is higher than solvent as evident from the above figure. Being a colligative property is proportional to molality, i.e. where Kb is constant. If m equals Kb, the Kb is defined as elevation and boiling point of 1 mole solution. It is called molal elevation constant or ebullioscopic constant. Units of Kb. For numericals, Kb for water is 0.52 K kilogram mole minus 1 means 1 mole of a substance solute in 1 kilogram of water increases its boiling point by 0.52 K. Thus, boiling point of 1 mole solution in water equals 373 K plus 0.52 K equals 373.52 K. An aqueous solution of ethylene glycol is used as coolant in cars in hot regions. It raises the boiling point of water and decreases its vapor pressure. Thus, water evaporates slowly and lasts longer in the radiator. Depression and freezing point. Substance is the temperature at which the vapor pressure of its solid form is same as the vapor pressure of its liquid form, or in other words, the temperature at which its solid form is in equilibrium with its liquid form. When non-volatile solute is added to pure solvent, the freezing point of solvent lowers. Thus, depression and freezing point. Being a colligative property is i.e. where Kf is defined as depression and freezing point of 1 mole solution. It is called molal depression constant or cryoscopic constant. Units of for water is 1.6 K kilogram mole minus 1 means 1 mole of solute in 1 kilogram water depresses its freezing point by 1.86 K. Thus, freezing point of 1 mole solution in water equals 273 to 1.86 equals 271.14 K. An aqueous solution of ethylene glycol is used as antifreeze in car engines in cold regions. Freezing point of this solution is lower than the prevalent temperature. Thus, the water in car radiator does not freeze. Mixtures of ice and salts are used for producing low temperature for various purposes. Osmotic pressure. When dried fruits, beans and vegetables are kept in water, they slowly swell. This is because water enters through the skin of fruits and vegetables, and this process is called osmosis. Here, skin of fruits and vegetables act as semi-permeable membrane. Other examples of semi-permeable membrane are egg membrane, cellulose acetate membrane, etc. Flow of solid molecules through semi-permeable membrane towards solution is osmosis. To stop the process of osmosis, extra pressure is applied from the solution side. It is osmotic pressure. Closing parenthesis dot. B increases with concentration of solute, i.e. dot. I. Therefore. Or. Where R is constant called solutions constant, same as ideal gas constant. Where C is the number of moles of solute present in 1 liter solution. Used for determination of molar masses of polymers, proteins and other macromolecules, for which other methods, i.e. elevation and boiling point and depression and freezing point, cannot be used, as the changes produced in boiling point and freezing point are too small to be measured accurately, whereas the osmotic pressure generated is large enough for accurate measurement. Bioenergetics concept of free energy. Energy, some basic principles. The two concepts most basic to science are matter and energy. We shall introduce these concepts by defining matter as anything that has mass and takes up space. Energy, however, is more abstract. It can only be described and measured by how it affects matter. Recall that energy is the capacity to do work, that is, to move matter against opposing forces, such as gravity and friction. Put another way, energy is the ability to change the way a collection of matter is arranged. Forms of energy. Anything that moves possesses a form of energy called kinetic energy. Any moving object, including an atom or molecule, has kinetic energy, the energy of motion. Moving objects perform motion to other matter. A pool player uses the motion of the cue stick to push the cue ball, which in turn moves the other balls. Water gushing through a dam turns turbines. Electrons flowing along a wire run household appliances. The contraction of leg muscles pushes bicycle pedals. Heat, or thermal energy, is kinetic. Energy that results from the random movement of molecules. Light also represents energy, which can be harnessed to perform work, such as powering photosynthesis in green plants. Resting object, not presently at work, may also possess energy, which is the capacity to do work. Stored energy, or potential energy, is energy that matter possesses because of its location or arrangement. Water behind a dam, for instance, stores energy because of its altitude. Potential energy, a form of potential energy especially important to biologists, is stored in molecules because of the arrangement of the atoms that are bonded together. Energy transformations. Energy can be converted from one form to another. Chemical can be tapped when chemical reactions rearrange the atoms of molecules in such a way that potential energy stored in the molecules is converted to kinetic energy. Transformation occurs, for example, in the engine of an automobile when the hydrocarbons of gasoline react explosively with oxygen releasing the energy that pushes the pistons. Similarly, chemical energy fuels organisms. Cell respiration and other anabolic pathway unleash energy stored in sugar and other complex molecules and make that energy available for cellular work. The chemical energy stored in the fuel molecules had itself been converted from light energy by plants during photosynthesis. The free energy concept, a criterion for spontaneous change. How can we predict what can and cannot occur in nature? How can we distinguish the possible from the impossible? We know from experience that certain events occur spontaneously and others do not. For instance, we know that water flows downhill, that objects of opposite charge move toward each other, that an ice cube melts at room temperature, and that a sugar cube dissolves in water. But, explaining why these processes occur spontaneously is tricky. Let's begin by defining a spontaneous process as a change that can occur without outside help. A spontaneous change can be harnessed in order to perform work. The downflow of water can be used to turn a turbine in a power plant, for example. A process that cannot occur on its own is said to be non-spontaneous. It will happen only if an external energy source is added. Water moves uphill only when a windmill, or some other machine, pumps the water against gravity, and a cell must expend energy to synthesize a protein from amino acids. When a spontaneous process occurs in a system, the stability of that system increases. Unstable systems tend to change in such a way that they become more stable. A body of elevated water, such as a reservoir, is less stable than the same water at sea level. A system of charged particles is less stable when opposite charges are apart than when they are together. In situations less familiar to us, how can we predict which changes lead to greater stability in a system? Which changes are spontaneous? The concept of entropy teaches us that a process can only occur spontaneously if it increases the disorder of the universe. It's helpful in theory, but it does not give us a practical criterion to apply to biological systems because it requires that we measure changes in the surroundings. We need some standard for spontaneity that is based on the system alone. That criterion is called free energy. The concept of free energy is not easy to grasp, but the effort is worthwhile, because the idea can be applied to many biological problems. Free energy is the portion of a system's energy that can perform work when temperature is uniform throughout the system, as in a living cell. A system's quantity of free energy is symbolized by the letter G. There are two components to G, the system's total energy, symbolized by H, and its entropy, symbolized by S. Free energy is related to these factors in the following way. G equals HTS. T stands for absolute temperature, OC plus 273. Notice that temperature amplifies the entropy term of the equation. This makes sense, because, as we learned earlier, temperature measures the intensity of random molecular motion, heat, which tends to disrupt order. What does this equation tell us about free energy? Not all the energy stored in a system is available in E for work. The system's disorder, the entropy factor decreases the availability of energy to perform any work. How does the concept of free energy help us determine whether a particular process can occur spontaneously? Think of free energy, G in the above equation, as a measure of a system's instability, its tendency to change to a more stable state. Systems that are rich in energy, such as stretched springs or separated charges, are unstable. So are highly ordered systems, such as complex molecules. Those systems that tend to change spontaneously to a more stable state are those that have high energy, low entropy, or both. The free energy equation weighs these two factors, which are consolidated in the system's G content. Now, we can state a versatile criterion for spontaneous change. In any spontaneous process, the free energy of a system decreases. The change in free energy as a system goes from a starting state to a different state is represented by increment G. Increment G equals G final state, G starting state. Or put another way, increment G equals increment HT increment S. T stands for absolute temperature, in Kelvin units, K, degree C plus 273. For a process to occur spontaneously, the system must either give up energy, a decrease in H, give up order, an increase in S, or both. When these changes in H and S are tallied, increment G must have a negative value. The greater this decreases in free energy, the greater the maximum amount of work the spontaneous process can perform. This is a formal, mathematical way of stating the obvious. Nature runs downhill in the broad metaphorical sense of a loss in useful energy, the capacity to perform work. 2 laws of thermodynamics. The study of the energy transformations that occur in a collection of matter is called thermodynamics. Scientific word system to denote the collection of matter under study and refer to the rest of the universe, everything outside the system, as the surroundings. A closed system, such as that approximated by liquid in a thermos bottle, is isolated from its surroundings. In an open system, energy can be transferred between the system and its surroundings. Organisms are open systems. They absorb light energy or chemical energy in the form of organic molecules and release heat and metabolic waste products, such as carbon dioxide, to the surroundings. According to the first law of thermodynamics, the energy of the universe is constant. Energy can be transferred and transformed, but it cannot be created or destroyed. The first law is also known as conservation of energy. The hydropower station does not create energy but convert potential energy stored in water into electrical energy when falling water moves the turbines. The second law of thermodynamics can be stated in many ways. Let's begin with the following concept. Every energy transfer or transformation makes the universe more disordered. There is a quantitative measure of disorder, called entropy, whose value increases as disorder increases. We can now state the second law as follows. Every energy transfer or transformation increases the entropy of the universe. There is an unstoppable trend towards randomization. In many cases, increased entropy is evident in the physical disintegration of a system's organized structure. Consider, for example, the degradation of an unmaintained building. Much of the entropy of the universe is less apparent, however, because it takes the form of an increasing amount of heat, which is the energy of random molecular motion. In most energy transformations, ordered forms of energy are at least partly converted to heat.